So welcome to this today's session. So today we're going to discuss on the basics of vectors. Then we'll slowly move into the various concepts of vectors, and then we will move into the vector space. Let us switch back to our screen here. So let me clear this section here. You all can see this drawing page, right? Yeah. For example, now the basic operations on the vector, or there are two operations that we basically perform. So that is nothing but the addition and the multiplication are the basic operations that we'll be performing on the vectors, and then we'll combine them as a linear combination. For example, we have two equations. So for example, 2v plus 5w equal to whatever we are not writing now equals to, let us just consider the left hand side of the equation, then 3v plus then 6w. So this is our equation, so which might be equal to, on the right side maybe this is equal to -1, or then this on the right side we will see this as equal to, say, plus 3 itself. Now these two linear equations can be written in a vector form as v is equal to, now its coefficients or the components also we call it as, now this is 2 and 3 here. So likewise, so w can be written as, that is 5 and 6. So now the 2 and 3 are the two different vector components. It is not the same vector components. So it is written in this way. So basically we will look into this in much more details later. So here we are just telling that, so we are going to perform the two operations here. Uh, that is nothing but the addition and multiplication. So for example, if we write here, that is v plus w, it means we are adding the vector v with the vector u. So that can be written as, that is v plus w is equal to, it is 2 3 plus 5 6. So that may leads to a one more new vector here, that is 5 plus 2 is 7, and 3 plus 6 is 9. So we have come across a new vector here. So basically we are going to apply vector in most of the applications like game theory. Why? Because when we talk in terms of just equations, it will give different dimensions. So that means we have multiple planes. So we can imagine having two planes, we can even imagine having three-dimension plane, but it's very difficult to imagine or picturize the 4-dimension, 5-dimension. As the number of dimension increases, it means, as we are telling in the last tutorial, as the number of unknowns increases, as the number of equation increases, the number of unknowns also increases here. So then in that case the vector is the best method, where we can represent this in terms of a coordinates, and we can visualize this in a vector in a single plane with many vectors, and we can write so many whatever the unknowns we can find it, and we can picturize that. So this is about the introduction of this. Now so we have understood that basically the two operations that are performed on the vectors, that is addition and multiplication. So multiplication can be written in terms of like any scalar quantity that is multiplied. For example, this v equal to, I can write this as c into its vector components v1 and v2. So let me clear this and rewrite this again here. So for example, let us take a two-dimension vector here. So it is represented in a column form. So that is, for example, v is equal to in two vectors. So that is v1 and v2. So v1 is the first component and v2 is the second component. And likewise, w, we have w1 and w2, whereas w1 and w2, again, these are different components. We cannot add these two components. You can think there's w1 and w2 as the apple and orange. You cannot add it. It's separate things. Now if you want to add, then we are going to add with the similar kind of components. Then as I told before, then V equals W equals to, that will result in V1 plus W1 and V2 plus W2. So this is a basic addition operation. The idea is that whether we add or subtract, that is from V1 and W1 and V2 with W2. We cannot do that with any other row cross. Now scalar multiplication is basically a multiplication by any scalar value, means a single value with the vector. Now for example, if I write here the 2v, it means we are multiplying this 2 with the individual components of this vector. So that is 2 into v1 and 2 into v2. So likewise minus v vector, so it represents, it means it is minus v1 with minus v2. And here one thing we'll note here, that the sum of minus v and v will result in 0 vector. For example, if I write here, in this case if I write, that is v minus v will result in 0. So this 0 doesn't mean that it is actual the number 0, but it is the vector 0. It means its component is 0 and 0. It means now the vector components are, so this v1 and v2 is 0. So that is the meaning of it. So these are the two operations that are performed on the vectors, that is addition and multiplication. Now let us look into some special cases of these vectors, the special linear combinations, or sum, difference, 0 and scalar multiplication. Clear this, right? So if you write here as 1v plus 1w, it means we have two vectors, that is v and w, as we have written before. Then it is called as the sum of vectors. So this basic representation is that we call this as sum of vectors. Now likewise, if we subtract this, the one vector with the another vector, and you see the important thing here, the scalar quantity that is multiplying the vector v and w is 1. So this we call it as the difference of the vector. Then the 0 vector is that where the vector, any vector, if it is multiplied with 0, so such vector we call it as a 0 vector. Now for example, we are adding the two vectors which are multiplied by its scalar value, that is 0. So then this will result in the 0 vector. So this we call it as 0 vector. And the vector we see in the direction of v. Now what does this mean is that, for example, here I have some constant c which is multiplied to a vector v, and we have one more vector w that is multiplied with 0. It means the components of the vector w are 0, and we have only one vector, that is v, and since it is multiplied with c, now this vector is increased in the same direction. So now this we call it as vector cv in the direction of v. It means it will escalate in the same direction. Now if you represent this in terms of vector form, now let us represent this in terms of vectors. The two numbers arrow are represented as 0, 0, that is point in a plane. When we add the numbers and we visualize that as v plus w here, so we will see the vector addition head to the tail. Let us see this. Let me clear this and right here we'll take the two planes here, This we have done even in yesterday's class. Now we'll do a little marking here for this. Now let us consider this is 2, and likewise we'll do some marking on the another axis here, so we'll call this as 4. Now for example, we'll consider that one vector v is 4 and 2. So 4 and 2 means it is a point or the coordinate. Now that is 4, that is on this horizontal line, and 2 is on the vertical line. So the vector b has a point here. Now it has in this direction. Now the vector is moving in this direction, so this is v. So this is v is equal to nothing but its coordinates, that is 4 and 2. Now we have one more vector, that is w. So w is equal to, I'll write this as minus 1 and 2. So it means that I'm having this. Now the first component represents the horizontal line and the second component represents the vertical line here. So now minus means it goes in the negative direction. So I'll take the marking here. This is one marking. So minus 1 and 2. So it means it is somewhere here, the point. So this is this vector is going in the other direction here in that plane. So this is w. We can write this as minus 1, 2. So please read it as minus 1. It's not clear. Minus 1, 2. So now if I add these two vectors, then what happens, in which direction it will move? Now we'll get a resultant direction, that is v plus w. If we add, then it is nothing but 4 and 2 plus minus 1, 2. We'll get the resultant direction as, let's see what is the coordinate that we'll get. So we'll get 3 and 4. So I'll get this as 3 and 4. Then what do we get here? Where is the 3? Now here is the 3 on the horizontal line and 4. So this 2, 3 and 4. So if I take here, so it might be somewhere the point here. So then we'll get this. Now this forms a parallelogram. If you join these dotted lines here, so this forms a parallelogram structure. So this is v and this is the w, the new points here. So it means now we can visualize this. After adding a vector, we get a parallelogram, the linear combinations that we will get. Now likewise, if you subtract, what do you get? I'll leave it to you. You figure it out and you draw by yourself the difference of the vector. Yes, correct, Sindhu. So now this is the addition. So likewise, the difference also you can do it. You subtract it and see what is the resultant vector you will get in which direction. So now let us move this to 3-dimension case. Let me clear this. So let's move to 3-dimension case here. So it means we have the 3 equations and 3 unknowns. Now if we represent these 3 equations in terms of the vectors, then we have v here. I'll just change the color. Just like this. So I'll take v as say 1, 1 and minus 1, and we have w equals 2, 3, 4. Now we have 2 vectors here with the 3 components each. Now let us see in terms of xy plane and how does it look. Now let us add these 2 vectors, that is v plus w. What do we get here? We will get 3, we will get 4, and we will get minus, sorry, not minus, we will get here as 3. So how do we see this in a xy plane? So vector xy, and as well as we will see in xyz. Let us put this in the 2 planes as well. So first let us see xy plane, and then we'll put this in the three-dimensional case. So for two dimension, we'll just take 2 and 3. Then for three dimension, we'll take all the three components. So if you just take the two components, it means if I just take the 3 and 4, the first two components of this addition vector, so then I'll get this in the two axes on the xy plane like this. So 3 is, if I mark this here equally, so it will be 3, and 1, 2, 3, 4 somewhere here, so I'll get somewhere here. So this point will be like this. So this is my some new vector. So this might be 3 and okay, so that is used for different. So this will be 3 and 4. So likewise, let us represent this in terms of three dimensions. There are a couple of questions here. What is the picture of all combinations of C into U? So if you talk about C into U, it means it will fill the line. So for example, if you take any one vector, then it will fill a line. It means it is having one value. Now if you multiply CU plus DV, it means we have two vectors and we're adding. It means it's in a two dimension. It means it will fill a plane. And if we have that CU plus DV plus EW, then it means we have three vectors, so it means it will fill the three-dimensional space. So on the plane, so that we can see like this. Now for the first one, if this is the setting point 0, so then if you move in this side, it means the C, this is U direction. So it means if the C is positive, we will move in this direction. Otherwise, if C is some negative term, then we will move in the opposite direction. So this will be minus C into U. So likewise, with UV, we'll get vectors like this. So this will be our U, will be moving in this direction, and this is V. So it will fill a plane. So basically it will act in one plane. And if we take W one more, so now what happened is that it will fill the one more direction. So now it will fill the three-dimensional space. So that is what it means. Now let us look into the length and dot product. So the dot product, or the inner product of V in W, let's say that. Let me write here the dot product or inner product of V and W is number V dot W. So the dot product is the dot product is a zero perpendicular vector. This can also be called like this. Now for example, let us see, we have here, there is a vector. So if you're writing the vector in the row, we will write with the comma. So it is v1 comma v2, and w is equal to w1 comma w2. So now if we write v dot w, so that is means v1 into w1 plus v2 into w2. So this is the dot product of the vector. It means if you write in terms of like this, a vector form, and see if this is v1 and v2, and you're adding, if you're taking the dot product of this w1 and w2, it means we are multiplying the terms, that is v1 and the first components, and then we're adding this with the product of the second components, that is v2 and w2. If you take an example here, so if we have the v vector as 4 and 2, the dot product of this is minus 1 and 2, is nothing but it is minus 4. It means 4 into minus 1 plus 2 into 2, that is 4, so it will result in 0. So the dot product is a 0 perpendicular vector. In mathematics we used to say like 0 is always a special case. So for a dot product, it means that these two vectors are perpendicular. The angle between them is 90 degree. Okay. So it will not result in any parallelogram. So this is about the dot product. So whereas a dot product here, one more property of the dot product is that, so v dot product with w is equal to w dot with v, the both results in the same thing, and it doesn't make any difference. So likewise, if we have the three components, then I'll just give a quick look here in this case. So then in case of the three vectors, sorry, the two vectors with three components, so then for example if we have v, that is v1, v2, v3, and if we have w of w1, w2, w3, then its dot product v dot w will result in, so this is nothing but v1 into w1 plus v2 into w2 plus w2 plus v3 into w3. So this is the dot product result of this vector. So there is one more term here, that is the length of the vector v. So the length of the vector v is nothing but the square root of v, so that will be written as like norms. So let me write here like the length is written in terms of norms of v, or the other way is that, so we can take this as length, which is equal to the magnitude of v, which is equal to the square root of, is equal to the square root of v into v. So in two dimension, the length is the square root of v1 squared plus v2 squared. So the dot product v into v squared length. Now let us take an example here and see the dot product of v into v squared length. So then for example if you take, right, like this, v square, then it means we are multiplying by itself. For example we have the vector 1, 2 and 3, it means multiplying, we'll take the dot product of this, then its dot product will result in 1 plus 4 plus 19 equal to 14. So now its dot product length is equal to 14. So it means it is nothing but that is v into v is equal to, it's written in this way, that is v square, and that is equal to 14. So let us take a look at one more example here. A vector u, a unit vector u is a vector whose length equal 1. Then its u into u will result in what? If it's a unit vector, then u into u will result in 1 itself. So the example which I'm talking about here is that, so we have u is equal to half, 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 and half. So then it's a dot product u into u. What do we get here? So we are going to multiply with its own terms, and then we'll finally going to add it. So u into u is nothing but it is 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, which will result in equal to 1. So doesn't feel 1.5, 1.6. Number 1, 2, right angle, Pythagoras. Okay, here the simple Pythagoras theorem is applied for this vector. If the vector is 1 and 2, likewise there is a length of something which is so let us consider that the v is a vector point, that is v is equal to 1 and 2 in the 2-axis plane. So then the arrow in the right angle. So for example, if you write the plane here, so 1 comma 2 is some point here, so there's a point. I'll get this. Now if we complete this, so this is nothing but 1 comma 0 point, the coordinate, and this is 0 comma 2 coordinate, and this distance is 1 and this distance is 2. So then if you apply the Pythagoras theorem, then we can find this is equal to this square root of 5. It's a very simple component. Now if we v into v is what we can do here, is that the 2 points 1, 2 and 3. That's 14. This is what we'll get. Is one of the example here, so I'm looking at. The base vector is perpendicular at 0, 0, 3 to be this. Okay, now let us see this representation of this vector in terms of matrix here. So let us start with 3 vectors. So let us define this is equal to u as 1, minus 1, 0, and v as 0, 1, and this is minus 1, and w is equal to 0, 0, 1. So now their linear combination in 3-dimensional space can be like, in a general form, it is cu plus dv plus ew. So the combinations can be written like this: C, so where C is a scalar quantity, a scalar multiplication with vector u, plus d of 0, 1, minus 1, plus e of 0, 0, 1. So then if we add all these vectors on the right hand side, we will get, if you see here the zeros, so then we will get this as C. Then we have what do we get here? We can write this as D minus C, because here it is D and here we'll get minus C. And then in the final equation we'll get here as E minus D. So we write this combination using matrix. Now if you rewrite this using the matrix, now this is the normal column vector representation. Now if you write these coefficients in terms of matrix, now it is 1, 0, 0, this is minus 1, 1, 0, and this is 0, minus 1, 0, and its unknowns are C, D, and E. So now we got one more interpretation here. So in normal way, in the equations where the C, D and E can be called as the unknowns, or also it is nothing but it is a scalar quantity for the respective vectors. It means it is C times the column vector 1, it is D times the column vector 2, like that we can interpret this. So then it results in the same thing. So this is C, and then D minus C, and E minus D. The number CD are the components of the vector X. So this on the right hand side we call this as the vector, sorry, not this one. So whereas this is nothing but the CDE, we call it as a vector X. So now in a general form, so let me clear this section. So if you write the C, D and E as a vector, for example C, D and E, if this is one column vector and this is represented by a vector X, so then the matrix A times the vector X is same as the CU plus DV plus EW. So let us see that. So it means the representation is AX is equal to, it's the same thing, so that is UVW, and this is C, D and E. So then we'll get this is equal to CU plus DV plus EW. So C, D and E are the multiplying vectors here. So now the matrix is multiplying these numbers. So the matrix A acts on vector X. So this is a very important point here. So if I write here, then the matrix A acts on the vector X. The result AX is the combination of P of column A. So it means, if you continue with the same example, the result AX is the combination of, let me write here then, the result A into X is a combination of is a combination B of the columns of A. Columns of A. Now let us take an example and understand this. Let me clear this section here. So x1, we'll use the terms x1, x2, x3 instead of CDE, and b1, b2, b3 for the components of AX. So then I can write this AX can write this Ax equals, I'll take one matrix 1 0 0 minus 1 1 0 0 minus 1 1. So if this is multiplied with x1 x1 x2 and x3, then that is equal to, so that will result in, what do we get, x1, then we have minus x1, so I can write this as x2 minus x1, and this I'll get it as x3 minus x2. So this is nothing but, I can call this as one more vector, that is b. So that is nothing but, we have the components b1 b2 and b3, so which is nothing but a b vector. So therefore the input x and the output is, the input is x and output is nothing but b, which is equal to a into x. This a is a difference matrix. This a, what we are talking, is the difference matrix, because b contains the difference of input vector x. Exactly. So this is basically a is a difference matrix, because if you see in the final resultant, so it is x2 minus x1, it is x3 minus x2. So this is how we can represent. So whereas in the top case only there is x1, it means we are subtracting x1 minus x0, which is equal to 0. So let us take an example and say this with x values. So now we will give input as x to this difference matrix. Then what do we get? Let us take the same difference matrix here. So that is a, we have the same thing, that is 1 0 0 and minus 1 1 0 0 minus 1 1. So now I'll take my x values as 1 4 and 9, that is the square numbers 1 4 and 9, where the square of 1 2 3. Now let us take this, what is the let us find the output. Now ax is nothing but the difference of this. So now if you look into this, so this is 1. Now the second component is nothing but it is 4 minus 1, and third component it is 9 minus 4. It means we are taking the difference of the second component here in x with the first component. So this will leads to 1 3 and 5. So this we call it as b, and output. Now let us look into the dot product with rows. How does it look like? Now if you want to write this in a very general way, the dot product, then we'll wind up the session. Dot product with rows, then it is something like ax is equal to, we'll take the same a here, that is 1 0 0, and this is minus 1 1, and this 0 and 0 minus 1 1, and when we take this as x1 x2 and x3, then it is something like this, and it is 1 0 0 with x1 with a dot product here of x1 x2 x3 separated by commas. So likewise it is minus 1 1 and 0 separated by comma, dot product of x1, x2, x3, and the last one is 0, minus 1, 1, with the dot product x1, x2, and x3. So this is a general form of writing dot product in terms of rows. Now let us look into the linear equations in the next class. So we'll wind up the session here. Thank you.